And this will be the bulk of the notes for polar calculus. I think I'll fit it all in this one video, or at least that's my plan. So let's just call this polar curve calculus. And the two things that we know how to do in calculus basically are slopes, that's derivatives, and areas, integrals. To do this, we're going to use a very consistent method that will tie this problem to another problem that we already know how to do. The method is to turn a polar curve into a parametric curve. And we already know how to do stuff with parametric curves. Although the area thing, we have to work that up a little bit more. So our method, turn polar curve into parametric curve. So for a polar curve, which we would write r is equal to some function of theta, right? Some stuff happening to the theta. Maybe it's r equals sine theta, maybe it's r equals I don't know what happening to theta, right? But you could write it as r equals some function of theta. We know that if we want to connect this to x's and y's, remember that x is equal to r times cosine theta, and y equals r times sine theta. So the parametric version of r equals f of theta is x is equal to r. It's this, but the r is that function of theta. So it's that function of theta times cosine theta, and y equals f of theta times the sine of theta. So that's really just the r, right? R cosine theta, where r is like whatever this is happening over here. And that means that dy dx is equal to, just like we did this, it's dy dt, but here I don't have t's, I have thetas over there. So like my parameter here is called theta instead of t, but what's in a name, right? I mean, the calculus is the same. So the theta is the name for the parameter instead of t. And remember that for a polar curve, the slope was dy dt over dx dt. So now we're just going to do dy d theta over dx d theta. And dy d theta, well, that's a product. So if I wanted to do it in general, I would have the derivative of this, which is the derivative of the first, f prime of theta times sine theta, plus the first times the derivative of the second, and then dx d theta. Notice I'm not doing the quotient rule, right? I'm just doing what's dy d theta, what's dx d theta. Is the first derivative of the first, rather, times the second, and then the first times the derivative of cosine is negative sine theta. So that's how you find the slope of a polar curve, and that's just a nasty looking formula that I highly discourage you from memorizing, because what you really want to memorize is that this is what we're doing once you have your x equals and y equals. So let's do an example. know why I wrote the whole word example out there. That's weird. I usually write just EX. Who knows? So find the equation for tangent line to the curve r equals 2 cosine theta at the point where theta is equal to pi over 3. All right, well, tangent lines we know how to do. That's all x's and y's. So I need a slope and I need a point. So let's find the point first. And let's first say I know that x is equal to r times cosine theta. And so if you wanted to write that out, you could write it's r, which is this, times cosine theta. So there's another cosine theta. So are you okay with that? Right? That's what the x would be. And then y is equal to r, 2 cosine theta, times sine theta. And you don't have to recognize this, but it sure saves you some trouble if you do, that this is the sine double angle formula. 2 sine theta cosine theta, that's the same as sine of 2 theta. You don't have to recognize that, but if you do, it's going to save us some trouble when we take the derivative. It's going to cut out the whole product rule thing. In this one, since it was 2 cosines in there, I can do this using the chain rule, right? Because that means the same as this. So I think in this form it's going to be a little bit easier for me. That doesn't always happen. Sometimes you just have to do the product rule. So dy d theta over dx d theta to find my slope. This is how we find dy dx. So be careful. It's such a common mistake to put these upside down because we always do x first. So make sure you do this one on the top. So the derivative of this, dy d theta, is derivative of sine is cosine of 2 theta times the derivative of what's inside. That's it. That's all I needed to do there. And then on the bottom, dx d theta, let's see, the derivative of something squared is 2 times that something, so that's going to be 4 times cosine theta times the derivative of what's inside, which is negative sine theta. And if you recognized that this was sine of 2 theta, maybe you recognize that this, again, you don't have to, but it's going to be a little easier, that this is the 2 times sine 2 theta. And there's a negative sign, and the 2 over 4 would cancel out to be a 1/2, but there's another 2 that's going to come out here because that's the cosine double angle formula. So I'll leave you to try to confirm that this is really the truth. And I think that that's right. Right? Because this would cancel. Leave a 2 here, but 2 cosine theta. Oh no, that shouldn't be there, should it? The 2 cosine theta sine theta, that is that. So there's no 4 there at all. There's nothing there. Right? That's just the 2 that I needed to make it the double angle formula. So I'm glad I checked that. And you could also, if you wanted to, say that that's negative cotangent, right? Cosine over sine of 2 theta, but I don't think that's really going to help us evaluate it, so I'm going to leave it like that. Okay, so now I need a point and I need a slope. So my point, if I use this here, the x-coordinate is 2 times the cosine of pi over 3, which is 1/2, squared. And that's equal to 1/2. My y-coordinate is, if I use this, you could use this one, but this is a little easier. It's the sine of 2 pi over 3. A sine of 2 pi over 3 is the square root of 3 over 2. Yes, you need to know this trig stuff. It's a thing. So there's my point. Point's 1/2 comma square root of 3 over 2. Now I need my slope. And I have my slope formula here. So that's negative cosine of 2 theta. So the cosine of 2 pi over 3 is negative 1/2 over the sine of 2 pi over 3, which I just did over here. So the negative signs cancel, the 2's on the bottom cancel. So the slope is 1 over the square root of 3. Right? So my equation for my tangent line in point slope form is y minus the square root of 3 over 2 is equal to the slope times x minus 1/2. And there's no reason to try to simplify that any further than that. That looks good. So there it is. I mean, that's a little bit more work than maybe what we're used to do for finding an equation for a tangent line, because we started with polar curve, we had to parameterize it, and then find that derivative, and then on top of all that, you had to plug pi over 3 into the trig functions to get those values. It's a tour de force of calculus and pre-calculus knowledge that you can bring to bear on that. If you wanted to check this, then could go back, and it would be a little bit of work to do. Let's see. Do you really want to see it or not? I guess the trick is that to check it, I'd like to see this circle. This is a circle, right? It's like the example we did in the first polar review notes, just with everything doubled. And I'd have to graph this and this on the same screen, and they're in different modes. So how to do that? You'd have to switch one of them to the other mode. So if I recognize that this is the curve, this is the same as, you don't need to write this in your notes, I'm just going to check this so I can show you. This is the same as a circle. Now instead of starting at 1, it goes out to 2, so it's this circle here with center at 1, 0 and a radius of 1. So that would be the circle x minus 1 squared plus y squared is equal to 1 squared. Right? And if I want to graph the top half of that, I could just graph and do the square root the other side. So in other words, I'm going to graph, so y squared is equal to 1 minus x minus 1 squared, and take the square root of that, right? And don't go doing bad algebra on me now. That does not mean it's just 1 minus that thing. You cannot do that when there's a plus or minus there. It's not the same thing. All right, so let me go back to function mode real quick and show you that we're good here. So, whoa, what's that? Garbage. So here I want the square root of 1 minus the quantity x minus 1 squared. And let's see. I'm not going to hit graph until I look at my window. So my window, I could just go from 0 to 2, and then my y values. I'm just going to graph the top half, and I know my tangent line is a tangent line to a point in the top half. So I go 0 to 2 there also, and graph that. And I kind of want to see that as really the top half of a circle. So I'm going to square the window again. Zoom square. So it looks more like the actual top half of a circle. And when I look, my point here at theta equals pi over 3, that's somewhere over here. And I have the coordinates, right? It's the point 1/2, comma, square root of 3 over 2. So it's right about there. So I should see it, if I graph my line, I should see a tangent line right to that point there. So let's go ahead and try graphing what we got and see how it looks. So y equals 1 over the square root of 3 times x minus 1/2, and then I need to add this to the other side, plus square root of 3 over 2. And the 2 should not be under there, so I always do that. Over 2. And there it is, our tangent line. Pretty. And let's see, do I want to do the area in this video as well? I think maybe I want to make that a separate video. So that's how you do slopes. And I'll cut this one off so we can have it stand alone as that. And we'll do areas in another one.